So as I said, what we're doing with comparing two samples to each other is each group has its own mean, and you're testing to see if there's a significant difference between those two. Like, let's pretend that there is a new prescription drug that you're trying out, okay? And you're comparing it to the existing treatment. Okay? We have a treatment group and we have a control group. So there's some sort of measure to compare how effective these treatments are. And you have a sample for your treatment, you have a sample for your control, the existing treatment. And you're testing to see if you get results with this new drug that are consistently better than the old drug. If they work the same, then there's going to be no significant difference between these two groups. But if this new treatment is actually better, you would expect these values to be consistently higher or to be consistently lower, depending on what you're measuring, than the existing treatment. Okay? So that's what we're doing, and this is really what statistics is meant for, is to be able to compare two different samples to one another. Now, as I mentioned, this is a little different than the paired t-test that we had talked about last week. With the paired t-test, you're kind of limited in that you're pairing one individual to another or subjecting that same individual to multiple treatments. That's very rigid in what you can do with that. You have more freedom in what you can compare with a two-sample t-test. Okay? So we're going to be looking at what those differences are and eventually performing two-sample t-tests and confidence intervals. Now, again, a little bit more background here. Two-sample problem can arise from a randomized experiment, comparative experiment, that splits the subjects into two groups and exposes each group to a different treatment. Comparing random samples separately selected from two populations is also a two-sample problem. And this is usually what we will do. Unlike the matched pairs design that we talked about last week, there is no matching of the individuals in the two samples. Now, the two samples are assumed to be independent of one another and can be of different sizes. This is important. Okay? We need independence. It's not like if you respond one way, you're in group A, and if you respond the other way, you're in group B. That doesn't work for a two-sample analysis. We need to have total independence between the two samples we're comparing. Secondly, with the match pair design, because you're kind of directly comparing individuals to each other, you needed to have equal sample sizes. Okay? And that was exhibited with the calculation of those differences that we did in like the chimpanzee problem. We can have different sample sizes with these T procedures, which is a big plus. Okay? Now, we'll talk at the end of class about how we want to make sure that we're not like deliberately going for different sizes. It's not like you're putting all of your eggs into the treatment group basket and then thinking, well, I better compare this to something, so let's get 10 people for our control group. No. Ideally, you want to try to target that they are the same size or approximately the same size. Okay? That's when these procedures work best. It says the most common goal of inference is to compare the average or typical responses in the two populations. So our conditions are pretty much the same as when we had a single sample, except with a couple of considerations that we just discussed. And we could have two random samples from distinct populations, and we do want that randomness. The samples need to be independent of one another, and we already mentioned that. Okay? One sample has no influence on the other sample, and you're measuring the same thing from both samples. Now again, just like we saw with a single sample, the goal is that they are both normally distributed. However, because we don't know the mean and the standard deviation, In practice, it's okay if we have just a similar shape between the two, somewhat symmetric, and that we have no strong outliers. And if we do have the presence of outliers, the bigger the sample size, the better. Now, we're comparing two different populations to one another, and each population is going to have some statistics that we're trying to find. Okay? It has its own variable, x, but it has its own mean and its own standard deviation. So our language for the hypotheses is with respect to the population. So we're going to be using these subscripts to represent our two populations and our two samples. Okay? Population 1, population 2. Okay, so we have mu1 for population mean 1, mu2 for population mean 2. Same thing for sigma 1, sigma 2 for the standard deviations. Now, we're pulling data from our sample, so a tweak of the notation here, we have two different sample sizes, two different sample means, two different sample standard deviations. And our goal is to perform an inference about the difference between those two means. And mu1 minus mu2, and to do that, we're comparing the two sample means, x bar 1 minus x bar 2. It doesn't really matter which one is 1 and which is 2. Typically, you want the larger value first, but you need to be consistent. So make sure that you have this sample mean going with this sample size, going with that sample standard deviation. You never cross them. Okay? That's one thing you have to be careful of if you're doing the calculations by hand. Okay? It's important for using technology as well, but it's kind of more difficult to make that mistake because you're just entering the important values. So, to tweak our procedures for two samples, what we're doing is changing our standard error calculation. Now remember that ideally we had sigma over the square root of n when we're calculating our standard error. That was how we fit our step size on our normal distribution of the samples. But now we have two different samples and two different standard deviations. So essentially what's happening here is we are finding an average of the two. Okay? We're kind of putting them together. I want to use the word pooling them together, but that means something different, so I don't really want to use that word. Okay? But we're putting them together and averaging them out. And algebraically, what's going to happen is that you're going to have a standard deviation 1 squared over its sample size and standard deviation 2 squared over its sample size. And then you're taking the square root of all of that. Okay? And because we don't know the population standard deviation, we are going to replace that with our sample standard deviation, S. So what happens is we have S1 squared over N1 plus S2 squared over N2, and take the square root of that. This is our standard error for our two sample T procedures. Now, you can already see that it's starting to get a little bit more complicated with our calculations. Okay? This was easy enough to keep track of, but now, two different standard deviations, two different sample sizes, and don't forget about that squaring of the standard deviation as well. That's a common mistake that I see when people are trying to do these calculations by hand. Okay? Again, I advise you to let the technology take over. We'll look at that. So, when you put this into the calculations for our T statistic, what we are finding is this is all based off of our standard Z procedures, where we did x minus mu over standard deviation. Well, now our standard deviation is that standard error calculation that we just talked about. Our value is x bar 1 minus x bar 2. And our expectation is the difference in the population means. Mu1 minus mu2. Now, don't write down this equation because we're going to clean that up in a minute. Okay? And I do plan on kind of collaborating or pulling a big equation sheet together for you, okay? That I will get to you. But with this, think about what's going on with these mu's. We are trying to say that there is a difference between these two samples and ultimately between these two populations. What this mu1 minus mu2 is saying is it's finding that difference. And as part of the null hypothesis, we are saying that they are the same, that there is no difference. So what's going to happen is we're going to replace that with a 0, okay, which cleans this equation up a little bit. Now, over the next few slides, you're going to see this like option 1 versus option 2. Option 1 is using software, technology, either the calculator or GeoGebra. Option 2 is doing things by hand, the calculations, and using the table, which I'm going to explain a little bit more about the table today, because I think some people were having some questions, but I think that will show you that it's more complicated than just using the calculator. Yeah, so we'll get into that in just a moment. One thing with the degrees of freedom, remember how degrees of freedom, sample size minus 1? Well, now you have two different sample sizes. So if you're doing this without the technology, it's a little bit less precise, but you're going to look at the smaller of the two sample sizes and do n minus 1 with that. Okay? That will help you get in the neighborhood of the correct p-value. So if you had a sample of size 30 and a sample of size 20, you would go with the sample size of 20, 20 minus 1, 19 degrees of freedom. Now for a confidence interval, the procedure is still the same. You're taking your sample value plus or minus whatever this t star is times that standard error value. We've already talked about where this standard error calculation comes from. T star is going to come from the chart that you get by using this equation. And then x bar minus, or x bar 1 minus x bar 2, that is the difference in your sample means. Okay? So your first sample has some average value. Your second sample has some average value. Big minus small is usually the way it goes, and that is the center of your confidence interval. Let's take a look at the hypothesis test as well, and then we'll look at an example problem to kind of walk us through these procedures. Now, the null hypothesis for these procedures is always going to be that the two population means are equal to each other, that there's no difference between them. I'm going to say something that I'll probably be saying a lot over the next several days. A difference of 0 means there's no difference. So the null hypothesis is saying that there's no difference between the treatment group and the control group, that they are the same. The alternative hypothesis is probably going to be something along the lines of like, the treatment group is better than the control group, that you have a higher average than the expected treatment, okay? That your new drug performs better than the old one. The null hypothesis is that they perform equally. This is different than what we've done before. Previously, we've been saying that the null hypothesis is equal to this value, that there is some number that goes in for that null value. That the average blood pressure at the company is 120 or whatever. You feel that your company's blood pressure is actually less than that. Now you're getting to be able to make direct comparisons between things, and you don't need a value. But look at what happens with, if you're saying that these two numbers are the same, remember previously on our T calculation, we had this minus mu1 minus mu2. But if these are the same, let's say they're both 5, mu1 is 5, mu2 is 5, 5 minus 5 is 0. So you have this minus 0, and this goes away. All you need in that numerator is x bar 1 minus x bar 2. Okay? It allows you to test to see if there is a difference, divided by that standard error calculation. I know this is all theoretical right now, but any questions about those procedures? All right, so let's look at an example problem as kind of our walkthrough here. So people gain weight when they take in more energy from food than they expend. Makes sense? Dr. James Levine and his collaborators at the Mayo Clinic investigated the link between obesity and energy spent on daily activity with data from a study with both sample sizes as 10 health volunteers. So these are both samples of size 10. Again, with these procedures, you don't need the samples to be the same size. Ideally, you want them to be either equal or approximately equal. So 10 of these people were lean, and 10 of these people were mildly obese, but still healthy. They wanted to address the question, do lean and obese people differ in the average time they spend standing and walking? Okay. So this is a bit of an observational study, right? You're looking at people go about their daily lives, okay? Go to work, come home, and they're keeping track of how much time are they standing or walking, how much time are they on their feet, versus how much time are they sitting, versus how much time are they lying down. And you're trying to see if there's a significant difference in the activity levels between the lean people and the obese people. So we are going to use a 90% confidence interval, a little different than what we're usually using. 90% confidence interval for mu1 minus mu2, the difference in average daily minutes spent standing and walking between lean and mildly obese adults. Now, we want to verify that we're allowed to use these procedures with our conditions. Okay? Now, examination of the data reveals all the conditions for inference can be at least reasonably assumed. Okay? Yeah, the distributions are a little bit small, only 10. It's kind of to be expected, and I'll show you the shape of the distributions momentarily here on our next slide. So here is our raw data. We have our two groups. We have lean as our first 10. We have obese, or they said mildly obese, for our second 10. Now, the raw data measured 3 different categories: standing and walking, sitting, and lying down. For our analysis, we are only going to look at the amount of time spent standing and walking. So we are looking at the first 10, and these numbers are for the lean group, and the second 10, these numbers are for the mildly obese group. And that data is summarized here on this back-to-back stem plot, where we can see that the obese group tends to skew a little bit lower, but there's no real extreme values there. It's approximately normal. A little bit more variation with the lean group, but still somewhat symmetric, somewhat normal. across our sample size of only 10 for each group, it's thought of as being good enough that we'll continue on with our procedures, our T procedures. You might have a little bit of a question about the randomness of this. It did say that these participants were health volunteers. Now, we don't know a ton about the way this was conducted, but health volunteers, maybe we're a little bit suspicious that, like, do they volunteer at this health clinic? Are they employees of this clinic? Are they all doing the same basic activities every day or same job every day? We would like an assurance of the randomness. We said that that is what's important for your sample, is that you have that element of randomness. But we'll give a little bit of leeway here and say that, all right, we'll assume that this is conducted in a well-done manner and that those health volunteers are obtained randomly. Now, we will look at the confidence interval first, but when we do our hypothesis test, here are our hypotheses. The null hypothesis is that mu1 equals mu2. That the average amount of time spent standing and walking is the same for the lean group and the obese group. Remember, this is sample 1, this is sample 2. We are theorizing in our alternative hypothesis that the lean group is spending more time on average standing and walking than the mildly obese group. We have enough of an idea that it's not going to be less than, so we're not going to test this as two-sided. We're going to go into this as a one-sided alternative hypothesis. Any questions about that? Okay. Notice that there is no number as part of the null hypothesis. That is a noticeable difference between what we've done in the past with our single sample procedures and our two sample procedures. Instead of comparing your sample to a number, you're comparing one sample to another sample. So, in this case, we have the descriptive statistics provided for us. It finds, well, the sample size we know, but the sample mean for both the lean and the obese group, and the sample standard deviation for both the lean and the obese group. And in a second, I'll show you what you'll be doing on the calculator or with GeoGebra to get these values if they're not provided for you. But these are the numbers that if you are calculating this by hand, this confidence interval by hand, I mean, look what goes into this. Okay, big mean and small mean, that is x bar 1 and x bar 2. So you're doing this 525 minus this 373. That is grouped in parentheses, plus or minus this t star calculation. So again, for t star, you're doing that equation of x bar 1 minus x bar 2 over the square root of sample standard deviation 1 squared over n1 plus sample standard deviation 2 squared over n2. You're doing all of this as part of that t star calculation. I'm sorry, that's part for our measure of variability, our standard error right here. For this t star, we are going to the chart. So, sorry, I'm getting backwards on myself here. I have this chart provided for you. I printed this out. I'll pass it out to you. I do have it directly linked to this one-page PDF on Canvas. If you prefer to use that rather than have this paper, that's fine. But those of you at home, you can take a look at that. I'll bring it up right here. But I'll pass it out. If anybody does not want this, just let me know. Okay. Now, we're working with a sample of size 10. Yeah, 2 samples of size 10. So that means that we have 10 minus 1, 9 degrees of freedom. Here is our T-star chart. So, the way this works. Across the top, we have our level of confidence. Remember, for this problem, they chose only a 90% level of confidence. So we're going to go from this column right here, this 90%. Along the left side, we have our degrees of freedom. So there are 9 degrees of freedom. So we're going to line these 2 columns up, or the column in the row up, and we get 1.833. That is our T-star, this 1.833. So we would come back together over here. There's our T-star, 1.833. That's what goes right after the plus or minus and before our standard error calculation that I was talking about before. Actually, for that, you don't need that. You just need the big old square root right there. Okay? So, it's a little bit more complicated than using the technology. Let's take a look at the technology, though, because this is going to be pretty straightforward here. So, okay, so on the calculator, I don't have data entered into the lists, but you have 2 samples. So you want to have data in L1 and data in L2. So I'm just going to put some quick data in here. So this would be sample 1, this would be sample 2. Now back on the main screen, you can go stat, calculate. Rather than 2 var stats, you can just go to, or I'm sorry, rather than 1 var stats, you can go to 2 var stats and just confirm that your lists are L1 and L2. And you can quickly and easily get, and this looks pretty similar, X bar is your sample mean for the first group, sample standard deviation. These are not accurate for our problem. And then you scroll down, and you have Y bar and SY for your sample mean for your second sample and your second standard deviation. Okay? So you can go with those 2 values, and then when you're calculating your confidence interval, we're going over to tests, and then, over to tests, and scroll down. We want a 2-sample T interval. So on your calculator, it's number 0, which is like number 10, for a 2-sample T interval. And once again, you can have it pull from the data that's in your lists. That's probably the easy way to go if you have a raw set. Or, remember, they gave us all the critical values on that table right there. Some of the problems and some of your homework problems will give you both sample means, both sample standard deviations, both sample sizes. You can just feed all of that data into this stats tab, X bar 1, SX1, N1, X bar 2, SX2, N2, and then our level of confidence, we wanted 90% in this case. You're going to leave this as no when it asks you for pooled. Okay? I'll talk more about that later. Okay? And then you calculate your confidence interval, and it will give you some numbers. Okay? With GeoGebra, what you're doing is using your sample data. Now, I got this from the spreadsheet of shared data that I reference on your homework. And I put our sample data in column 1, or column A and column B. And these are the two. A is the lean values, B is the mildly obese values. And I copied those and pasted them in here. I'm going to perform a multiple variable analysis, which is the equivalent of the 2-var stats on the calculator. So you do this multiple variable analysis, and it'll give you a box plot, which kind of helps you with the visualization of the two data sets. But really what we want are the values down here on this chart. If that doesn't come up immediately, you have this sigma x button right here to give you the descriptive statistics. We want the 2 sample means, the 2 sample standard deviations, and we already have the 2 sample sizes. And we're going to take those values and go over to the probability calculator. And remember, here's our distribution page. We want this statistics on our probability calculator. And from our menu of options, we've already done z-test and t-test, z-estimate, t-estimate. We want t-estimate of a difference of means. This option right here. We want a 90% confidence interval, so we enter that. Again, like we saw a question about pooled on the calculator. Do not check the pooled box for this. That's kind of an outdated, antiquated question. We don't need to worry about that. Now, here's a limitation of GeoGebra. We said with the calculator, you can have it pull means and standard deviations directly from the lists. Not so in GeoGebra. You do have to type those numbers in yourself. Okay, so what you probably want to do is just get like a little split screen going here. Okay. You've got your means there and your standard deviations. Okay. And just type those into keeping them organized. Here is our lean group, here is our obese group, for our comparison. But once you have all of that data entered, we get our degrees of freedom, which you'll notice is not the same as our n-1 that we did, because we went with 9. This is one reason why the calculator, or GeoGebra, is better. It's more precise. But we get lower limit and upper limit, and this is our confidence interval, 82.345 to 222.619. And that is our confidence interval. So let me go back to our presentation here. All right, so here is our summary screen on both the calculator and GeoGebra that we just saw. Let's talk about what this confidence interval means. Okay. Remember, we're doing x bar 1 minus x bar 2 to find a difference between the two samples. What this confidence interval is saying is that we are 90% confident that the actual difference is between 82 and 222. What is important about a confidence interval with a difference of two means is, does the confidence interval cross 0? I said it before, and here it is again. A difference of 0 means there's no difference. So what if this confidence interval was like negative 100 to positive 200? Now you're saying that, well, we're 90% confident that the difference is from negative 100 to positive 200, that the obese group is standing more than the lean group, is what a negative score would mean here, because you're doing lean minus obese. We did big minus small, so we expect our values to be positive, and because it's completely above 0, we're saying that, well, 0 is not on this interval. So we're pretty sure that there is a difference, and it's entirely going to be positive, that the lean group stands more on average than the obese group, and that difference is between 82 and 222 minutes on average. But if it crossed 0, now you're saying, well, there are some cases that we think that it's going to be the obese group standing more than the lean group. Now, if you had switched your X bar 1 and your X bar 2, and you had small minus big, then you're looking to see if your interval is entirely below 0. Okay? Just think about what you're doing. You do have the freedom in letting either sample be 1 or 2, but think about how that impacts your analysis and impacts your conclusions. Any questions on this so far? All right. Now for the t-test, same thing. On the calculator, you're selecting 2-sample t-test. GeoGebra, the drop-down menu is just difference of means for the t-test. And you're entering the same data. Remember, our null hypothesis was that mu1 equals mu2. Our alternative hypothesis is that mu1 is greater than mu2. On GeoGebra, they have it set up in that older format where mu1 minus mu2, we are testing to see if that is 0. Theoretically, you could say that you expect a difference of 20 or whatever number you want to put there. I will say for most, if not all of our tests, we're just going to leave that as 0 for our null hypothesis for a difference test. Our alternative hypothesis was greater than. Never check that pooled box. Okay? Same numbers we had before. We go through, we get our t statistic. We are 3.8 standard deviations or standard errors away from the center of this t distribution. Pretty big. Corresponds with a p-value of 0.0008. Look at the calculator. Same t statistic, this p-value, 8.4101 times 10 to the negative 4th. If you use the calculator for your calculations, be on the lookout for this. I can't tell you how many people I've had over the years go through all the work, and it's done accurately, but they look at this p-value, they say, oh, 8.4 is bigger than 0.05. I fail to reject the null hypothesis. Right? That's wrong on 2 different levels. First off, remember, p is a probability. It cannot be bigger than 1. And it is not. It's so small that it's in scientific notation. Okay? You know how scientific notation works. These 2 numbers, that and that, they are the same. You have 8.4 times 10 to the negative 4th. So you move that decimal point over to the left 4 places. 1, 2, 3, 4. And this is 0.0008, which is less than 0.05. So you do reject the null hypothesis and accept the alternative hypothesis. You have very strong and convincing evidence that yes, that lean group stands more, on average, than the mildly obese group. It would be very, very unlikely, remember, this is a probability, that you would get values like this just due to natural variation alone, if they are in fact equal. Very, very rare. Okay? That is the probability of your type 1 error, 0.0008. So I never want to see somebody say that a p-value is bigger than 1. No, no, no. Wrong. That shows me that you have no idea what's going on. Okay? If you see something like that, look to the end, see that it's in scientific notation. Questions here? Okay. Now, I have one more example problem, which we're not going to go through in as much detail, but I want to kind of show you some of the differences here. It says, do college students who have volunteered for community service work and those who have not, do they differ in how attached they are to their friends? So a study obtained data from 57 students who had done service work and 17 who had not. Notice, we have 2 different sample sizes, and that's okay. And ideally, we'd like them to be the same or close to being the same. We do have a lot of variation. They differ by 40 here. We'll go with it, though. As long as they're randomly obtained and they're independent of each other, should be good. So, one of the response variables was a measure of attachment to their friends. So they developed some sort of scale for measuring attachment to their friends, how close they are to their friends. The higher the score, the more attached they are to their friends. So in group 1, the service group, that group had an average score of 105.32. The non-service group, only 17 people, they had an average score of 96.82. So yeah, there's a difference there in the average score, a difference of about 9 points. Our test is to see, is that difference of 9 points significant enough to say that, yes, the service group has a closer attachment to their friends. Now again, clearly this is an observational study, okay, so there's all that stuff about causation that we can't get into, but from our observational perspective, we can get the, what's the language? Like, there appears to be a relationship or an association between these, okay? So, standard deviations for both samples set up our hypotheses. The null hypothesis for a difference is always going to be that the 2 are the same. Okay? The average score for the service group is equal to the average score for the non-service group. We go into this with no real idea that, yeah, we might think that the service group is higher scoring, but we'll take the safe approach, make it 2-sided. Okay? We're testing to see if there's a difference between the 2 in either direction. That's the safe way to go. So, if you were doing this by hand, and again, shows you how complicated the by hand procedures are. Here is our calculation for the t statistic. X bar 1 minus X bar 2 over that standard error measure. We're providing all of those values, our 2 sample means, our 2 sample standard deviations, our 2 sample sizes. Make sure you're matching them all up. Okay? All of these values on the left are for the service group. All these values on the right are for the non-service group. This works out to give us 8.5 is the difference right there, divided by this number. We get a t statistic of about 2.142. 2.142. Again, what this means, here's our little fatter tails here. Here's what we expect at the center as our difference. We are like right there, 2.142. And we're testing to see that and that. If there's enough data in those tails, to say that we're going to reject our null hypothesis? Well, the way we find this by hand is taking this t statistic of 2.142 and going back to our chart. Okay, on our chart. Now, we are not going to do the confidence interval in this problem, so you're not going to use these columns at the top. Instead, you're using these columns at the bottom. We have both one-sided and two-sided p-values down here. Remember, our alternative hypothesis was two-sided. So we're going to be going with this bottom row. But that's our final answer. Okay? Along the left side, we need to select our degrees of freedom. And we had samples of differing sizes. Our smaller sample was 17. So 17 minus 1, we have 16 degrees of freedom. Right there. What we are doing is looking in this row, trying to get as close to that t statistic of 2.142 as we can. So going across here. No. Here it is. 2.120 and 2.235. So we are between these two values right here. So we're going to take this to the bottom, and we see for our two-sided p-value, we have a p-value that is between 0.04 and 0.05. That is the best we can do by hand with the t procedures. Okay, so going back over here, our p-value is between 0.04 and 0.05, which means we reject the null and accept the alternative hypothesis. We have evidence that there is a significant difference between the two. We can be more precise if we use the technology, though. Okay? If we put this into the calculator or into GeoGebra, we get our exact p-value as 0.0414. And we didn't do all this stuff here, and we didn't have the chance of making a mistake, either with inserting the values, or, I will say, I see a lot of mistakes with people messing up the order of operations here. That's very easy to do. I mean, look at these fractions, look at these exponents, look at this big square root right there. It's not complicated to do by hand, but it's easy to mess up. Okay? Especially if you're trying to type all this in at once. Again, my suggestion, embrace the calculator for these calculations. Our interpretation here, it is worth noting that we are just barely below our 0.05. And they use the word, we have moderately strong evidence that there is a relationship. Yeah, we're going to reject the null, accept the alternative. Okay. But there's a difference between a p-value of 0.0414 and the p-value of 0.0008 that we had in our previous problem. This was very strong and convincing evidence. Remember what p is. It's a probability. It's the probability that the null hypothesis is true and that we would get this value that far away from what we'd expect. So in our previous example, it was very unlikely that we would get something like that as a fluke. In this case, for almost 5% of the time, we'll expect no difference, but get a difference of 8.5 like we got here. It happens. It happens 4% of the time. It's rare enough that we're going to say that we have evidence that there's a difference, but not nearly as strong as we did before. So use the language in your interpretation. It's a moderately strong difference. Questions with that? Good. All right, my last couple slides here. Just talking a little bit about the interpretation. I mentioned robustness last week. Remember, a procedure is robust even if you're not meeting all of those conditions, you get results that hold up, that they stand up, even if it's not like a perfectly normal distribution, or even if the sample size is kind of small, okay? Or even if you have some skewed values. Okay? The two sample t procedures tend to be more robust than one sample t procedures, particularly when distributions are not symmetric. Okay, so they hold up a little bit better than the one sample procedures. It does say when the sizes of two samples are equal and the two populations being compared have distributions with similar shapes, probability values from this table are quite accurate for a broad range of distributions when the sample sizes are pretty small as 5. But when the two population distributions have different shapes, larger samples are needed. Okay? So again, you'd like to be comparing apples to apples, right? But if you have an apple compared to a pineapple or a pear, you can still get away with it. It's not quite as robust, but still pretty good. A larger sample size, that's kind of like the cure-all for everything, right? Makes it a little bit better. It says, as a guide to practice, adapt the guidelines for one sample t procedures to two sample procedures by replacing sample size with the sum of the sample sizes. So, like if you have in your mind that you're targeting a sample size of 100 people, well, it's okay to split that 50 and 50 when you're looking at the two sample procedures. They give you a word of caution here. It says, in planning a two-sample study, try to choose equal sample sizes whenever possible. The two-sample t procedures are most robust against non-normality in this case. And the conservative option 2, doing stuff by hand, probability values are most accurate in that case. Okay. Again, you want to try to compare samples of equal size. Doesn't have to be perfectly equal, but in the same neighborhood or ballpark, that's good. What you don't want to do is put all of your time and your effort into getting your treatment sample and then say, oh, I guess I better compare this to something. Let's wrap up 10 people here. They'll serve as my control. Okay? That's not the way to do it. Okay? Put equal time and effort into getting both samples that should be approximately the same. I showed you that the degrees of freedom calculation was no longer an integer when you're doing this by hand. Here is a complicated equation for getting that new value. Don't worry about this. This is not going to be on your equation sheet that I'll give you. You're good with taking the smaller sample and doing the n-1 for that. In fact, I probably should have cut that slide. All right, last thing here. I mentioned when we were using the technology, do not check the box for pooled. Okay, or if it asks you if the data is pooled, say no. The calculators and the technology, they take this into account. Pooling data was like an old school method when the technology was unavailable to us. It would try to make the calculations easier by putting everything into one big sample, pooling it together. And the calculator allows you to be able to do that. Just don't select that. Okay? Never use the pooled t procedures if you have software technology that will implement the unequal variance procedure. Okay? Terminology that you don't really need to worry about. It's just a long way of saying do not pool the data. All right. Any questions here? I know that was a long, complicated lesson, but hopefully not too complicated. Again, try to differentiate between like what is brand new versus what have you already done. Okay? We know the basics of confidence intervals and these t-tests, these tests of significance, hypothesis testing. We have a slight tweak to our equations and procedures for comparing two samples to each other. But the basics of what we're doing, that has not changed. We've been doing it for weeks now. Okay? So on Wednesday, we'll practice a little bit of this together. Okay? Kind of clarify some things, start to work through this, and make sure that we're getting good with it. Okay? And towards the end of the week, we're going to start to look at proportions so we can analyze categorical data. Okay? Up to this point, everything has been quantitative. All right. So if that's all, we just have a couple minutes left. Hey, you guys at home, free to sign up. Have a good one. I'll see you.